Let's start today's video with a definition. The definition of a limit point. Let x comma tau be a topological space. Let A be a subset of x and small x be a point in x. Then we say that this point is a limit point of that subset A, or there are other names, a cluster point of A or a point of accumulation of A if for any open set U coming from the topology which contains that point, U intersects this set A from which x has been removed. That means this intersection is non-empty. That is, x is a limit point of A if every neighborhood of x intersects the set A at a point other than x itself. This U is a neighborhood of x because it is open and it contains x, and then it has to intersect A at a point other than that point x itself. If that happens, then we say that x is a limit point of A. Let's next see this example 8. In the space of real numbers R with the usual topology, if A is this half open interval, open 0, closed 1, then 0 is the limit point of A and so is 1 divided by 2. Let's see exactly why. In this case, of course, you can draw a figure, your familiar real line with the usual topology, in which the set A looks like this open closed interval 0, 1. Now we are saying that 0 is the limit point of A. So that means we now have to verify that. So you consider any neighborhood U of 0, which by definition is an open set in R containing 0. Now that can be of any type. There are many different types of open sets in R, in the topology on R. But no matter what type of set U is, inside U there will be a basis element containing 0, which is an open interval. Say this is that open interval. Because it's an open interval and this side of A is also open, so in order to contain 0, it needs to intersect A here at these points. So all those points are different from 0 obviously. So that's how 0 is the limit point of A. And now you can see that a similar argument works for the point 1 divided by 2, which lies here in the middle. So any open interval which contains it, which either is a small one like this or large, any type of open interval which has to contain 1 divided by 2 must intersect A, obviously. So that's why. And intersect where? Intersect at points other than 1 divided by 2. Such points exist. So that is why this is also a limit point of A. And the example continues. If we consider in the same space R, if we now consider this set B, the set of reciprocals of all positive integers, then 0 is the only limit point of B. And the reason is this: for any non-zero real number x, x has at least one neighborhood. X has a neighborhood that either does not intersect B at all or intersects B at only x. And you can understand that in this figure. Say your x is this point 1 divided by 2, which actually is an element in B itself. You can consider this neighborhood. This neighborhood intersects B at only this point 1 divided by 2. So that's why by definition 1 divided by 2 is not a limit point. Similarly for 1, similarly for any other point of B. However, if your x is a point which lies here somewhere but that is not in B, say it lies between this 1 over 3 and 1 over 4, this x, then also there will be a small neighborhood depending on the location of the point that does not intersect B at all. Inside that neighborhood there is no point of B. So no such point is also a limit point. But if you look at 0, for 0, no matter how small a neighborhood you choose of 0, on this side of 0, there will be at least 1 divided by n by choosing n sufficiently large. That is why 0 is the only limit point of B. This is not a rigorous argument, but at least you get the idea of why this is true from this figure. Then you can consider this other set C, which is the union of the singleton set 0 consisting of 0 and the open interval 1, 2. The set of limit points of C is this closed interval 1, 2. I leave it to you to verify how, why. Note one more thing, that 0 is not a limit point. Every point of R is a limit point of Q, the set of rational numbers. Whereas no point of R is a limit point of set plus, the set of positive integers. This set has no limit point. The set of all limit points of R plus, this is the set of all positive real numbers, is the set of all non-negative real numbers. That means all the positives come, they are limit points, and along with them 0 also comes. And then we have a result, theorem 17.6, where we are going to see how limit points are related to closures of subsets. Let A be a subset of some topological space X, and let A prime be the set of all limit points of A. Then the closure of A equals the union of A and A prime. To prove this equality, it's enough to show, and in fact that's the only way to show this, that each set is a subset of the other. So we first aim to show that the right hand side set, this union, is a subset of A closure. Now here we already know something. We already know that A itself is contained in A closure. Now we want to also show then that this A prime, the set of all limit points of A, is also a subset of A closure. And that's why we take any point X in A prime. This means X is a limit point of A. Then by the definition of limit points, every neighborhood of X intersects A. It's a different matter that much more is true, intersects A at a point other than X itself. But we now focus only on the fact that every neighborhood of X intersects A. And that is why by theorem 17.5, X belongs to the closure of A. And that's how any point in A prime is also in A closure. So we have this containment. So now you combine this containment and this containment. And from there you get the fact that A union A prime is contained in A closure. And now we will prove the reverse inclusion, that A closure is also a subset of this union. And as such, conversely, let Y be any point in A closure. Now if Y happens to be an element in A, it's a point in A, then obviously Y will belong to A union A prime. So that means now we have to consider the case where Y is not in A. Y is in A closure but Y is not in A. Then what's the consequence? This is the consequence. Since Y belongs to A closure, by theorem 17.5 again, because it works both ways, that theorem implies every neighborhood of Y intersects A, but at the same time, because Y does not belong to A, so every neighborhood actually intersects A difference Y. But then by definition Y becomes a limit point of A, so Y belongs to that set A prime, and that is why Y belongs to A union A prime. And that's how any point in A closure is inside this union. So this is also a subset of this. Combining this containment and the previous one, you have equality, and that's where the proof ends. And now we can link this notion of limit points with closedness of a set via this corollary 17.7. A subset A of a topological space is closed if and only if it contains all of its limit points. The proof is a fun little proof. A is closed if and only if A equals its own closure. We have already seen how this is true when we defined the closure of a subset. But just now we saw, that means our theorem tells us that A closure is nothing but A union A prime, the set of all limit points of A. But that union is equal to A if and only if A prime is contained in A. In other words, if A contains all of its limit points. So that's it. That's the proof. So this means in particular that if a set has no limit point, say A is the set which does not have any limit point, like that example. In the space of real numbers with the usual topology, the set of all positive integers has no limit point. So for that set, this set A prime is empty, so which obviously is contained as a subset inside the set. So that's why the set of positive integers is closed in R. This is a special case of this situation. Let's end the video here. In the next topology video, we are going to see Hausdorff spaces, a special type of topological spaces where open sets play the role of separating points in some sense. We will see other separation axioms also as we go further down the book.